So what we're going to talk about today is more conservation of momentum. Very specifically, though, the conservation of momentum for elastic collisions in one dimensions. It's a little bit of a mouthful, but let's go to some paper so we can talk about that. So let me share my screen and then we can get going. There we are. So what we're going to do here is we're going to look at what happens if I have two things that are going to collide. And like I said, we're going to constrain this to be one dimension. We're going to have them collide elastically. So what does that mean? Well, what that means is that when these two things collide, and whether that's object one, we'll call this object one, is moving towards object two and two is moving towards one, or two is moving to the right and also one is moving to the right and they collide, whatever the mechanism is, it doesn't matter. I'll just have some sort of initial velocity one and some sort of initial velocity two. In this case, obviously VI2 would be less in magnitude than VI1. Otherwise, it would never collide. But in order for them to collide elastically, what we have to do is consider the nature of the interaction forces that happen when one hits into two. So the important thing when we talk about this is we're going to describe something that's called a perfectly elastic collision. In a perfectly elastic collision, what's going to happen is the nature of the Newton's third law interaction forces during the collisions or during the collision is that the forces are conservative in nature. So normally when two things collide, like two cars collide, the two forces, the interaction force of car one on two and two on one, are going to be non-conservative. They're normal forces. But let's say instead I have a perfect Hooke's law spring here that's attached to object two, so that when they do that, what's going to happen is the spring is going to compress and then it is going to stretch out again, and we have conservative forces. Or maybe I have two magnets of like polarity here, like two north ends of a magnet, so they would get together, they would repel, never actually touch, right, and then go apart. But the nature of the forces is conservative, and that's going to have two implications. First, because all we have here is one on two and two on one, momentum, linear momentum, is going to be conserved, right? Because I have the net external average force on the system is equal to zero if all that is happening along this x dimension is the force of one on two and the force is two on one. There's nothing external to the system. I'm also going to have the idea that the work done by non-conservative forces in this interaction is going to equal zero because the forces of the collision are conservative in nature. And that's what it means to be a perfectly elastic collision. I'll come back to that perfectly elastic as opposed to just elastic in a couple of minutes after we do a little bit of work. So this means that momentum is conserved. So the initial momentum of the system is equal to the final momentum of the system. Now, if I'm being really specific here, which I guess I want to be, I am going to put an X on these. I'm going to drop the X subscript in a second because we are confining this to one dimension. But since we are going to do two-dimensional collisions elastic later, I just wanted to do that for sake of completion. What does this mean that the work non-conservative is equal to zero? Well, that means that the energy before the collision is equal to the energy after the collision. And so I'm going to define the moment before as I and the moment after as F. We'll talk about what's happening during that collision, either in another video or at the end of this one. So here we go. If I'm going to do this, it is a vector problem. I probably should have axes plus X because that's here, but I'm going to do this from a generic sense. We're not going to plug in values, but if I were, I'd be plugging in a positive VI, VI1 and a positive VI2 if I got down to this based on the way this problem is set up. Or if cart 2 is actually moving towards 1, I'd have the value, VI1 would be positive, VI2 would be negative, what have you. But what we're going to do here is, assuming I know what mass 1, mass 2, VI1, and VI2 are. Those are my knowns. What my job here is to predict and find out, can I figure out what VF1 and VF2 are? What is the final state of the two carts after this collision? And we're going to use these two equations in order to figure that out, which is great because I have two equations, two unknowns. I should be able to do it. So let's set these up. So I know that this is going to consist of the initial momentum of object 1 plus the initial momentum of object 2. And this is the final momentum of object 1 plus the final momentum of object 2. Once again, from a vector sense, but let's not belabor the point. We know these are vectors and we know these should all have X subscripts, but in the context of this problem, I'm fine. Here, well, what energy or energies does this thing have before the collision? Well, object 1 has kinetic energy, so the kinetic energy of object 1, and 2 has kinetic energy as well. And finally, they both have kinetic energy. And you may say, well, what about the spring? Well, the spring potential energy only comes into play during the collision, not the before and after the collision. So we will once again look at during the collision, because if I was comparing the initial energy of the system to the energy of the system during the collisions, I would need a spring potential energy term, but we'll come back to that. So here we go. Well, what can I do with that? Well, let's expand each of these to see what I can do. I have M1 VI1 plus M2 VI2 is equal to M1 VF1 plus M2 VF2. All right. Here I have 1/2 M1 VI1 squared plus 1/2 M2 VI2 squared is equal to 1/2 M1 V F1 squared plus 1/2 M2 VF2 squared. The reason why I had a little mental hitch is I was trying to remember if I did my number first or my state, initial final first. And I'm going to try to be consistent through this just so, but sometimes my dyslexia makes me jumble the order. The order doesn't matter, but it is nice to have consistency. So now I have two equations, two unknowns, and this looks just disastrous. So what are we going to do here? Well, one thing very easily we can do over in this equation, just to simplify, is I can get rid of the 1/2. I'm not actually concerned with the value of the energy of the system. So getting rid of the 1/2 doesn't really, hurt me in this case. But this would be kind of a terrible thing to solve if I'm solving for VF1 or VF2, specifically for what reason? Well, if you're sitting there thinking to yourself, oh, the squares in this just make it a disaster. You're right, because what I would have to do here seemingly is solve this equation for VF1 or VF2, plug it in there, FOIL it out, and you can just tell what an algebraic nightmare that's going to be. Gross. We don't want to do that. What would be even worse, though, is solving this equation for VF1 and plugging in here. Why? Well, hopefully what you said is we're going to get a square root here. That gives us a plus or minus. And that plus or minus is intensely problematic because this is a scalar expression as energy. And if you put that into a vector expression, that plus or minus changes all sorts of things. So that is absolutely not an avenue for approach here. So what are we going to do? Well, when we have complicated problems and just like the basic steps don't seem like they're going to work well, what we often want to think about is regrouping or restructuring our equations. So let's do that now. Let's see how this is all structured. Very clearly, both equations are structured by initials and finals, initials and finals. How about we restructure them by mass? In order to do that, I'm going to move everything 1 related to the left, everything 2 related to the right. So here we go, M1 VI1 minus M1 VF1 is going to equal M2 VF2 minus M2 VI2, okay? Similarly over here, M1 VI1 squared minus M1 VF1 squared is equal to, excuse me, M2 VF2 squared minus M2 VI2 squared. Right. You're like, okay, well, how does that make things better? Well, look at this. I can now pull out an M1. I've got VI1 minus VF1. I've got M2 VF2 minus VI2. Nothing really dramatic there. But here, VI1 minus VF1 squared is equal to M2 VF2 squared minus VI2 squared. And I'm just going to leave that there for a second. I want you to stop the video for a second and just think something about this structure sort of like tickling something in your brain. So just think about it for a second before we go on. So hopefully you stopped the video, you thought about it, and then you looked here and you saw these terms here and you said, oh God, that's the difference of perfect squares. Oh, okay. So I can do something with that. I can expand that out. So we're going to come over here and we're going to expand that out, and we're going to see why that is just absolutely fantastic. Okay, as soon as I don't become blurry anymore. There we go. So that becomes M1, and that's a VI1 minus VF1, VI1 plus VF1, and then this becomes M2 VF2 minus VI2, VF2 minus or plus VI2. And so if you look here, you'll notice M1 VI1 VF1, I've got that right here. M2 VF2 VI2, I've got that right here. So what I can actually do now is divide the two expressions. Whoever said that difference of perfect squares wasn't an amazing thing? Not me, an amazing thing. And so you'll notice a couple of things. First, the masses cancel, which is really nice. And the second, this term cancels, which is also really nice. And we're left with VI1 plus VF1 is equal to VF2 plus VI2. Now, that is a nice, easy link that we can use to solve this problem, and it doesn't have any squares. So what I'm going to do here is I'm going to use this equation in conjunction with our original momentum equation here in order to solve for VF1 and VF2. And then we're going to come back and we're going to talk about a couple of things, because this expression itself is really interesting, and I want to deal with that. But right now, I just want to continue with the problem. And then, as I said, in another video, we're going to deal with what happens in the collision itself. And we'll come back and talk about this expression itself as well, because that's going to help us think about what's happening during the collision as well. But just to keep this video concise and to the point. So, like I said, we're going to steal this equation here, and I'm going to solve it for, say, VF2. VF2 is equal to VI1 plus VF1 minus VI2. And we got to be very thoughtful and very careful here with our subscripts so that we don't mess things up. So I'm going to go back to this equation, and we're going to use that to plug in. I'm going to plug in VF2. So here we go. M1 VI1 plus M2 VI2 is equal to M1 VF1 plus M2, now I'm going to put in this term, VI1 plus VF1 minus VI2. Okay, now I'm not going to do too many steps of algebra at once. I am going to first just distribute that M2 VI1 plus M2 VF1 minus M2 VI2. Now remember, our goal is to solve for VF1. So I want to get everything that's not VF1 over on the other side. So here we go. You'll notice here I have two terms with VF1, and there's an M1, M2. So I'm going to actually just kind of flip-flop the terms here. So I'm going to have M1 plus M2 VF1, right? That's taking those two terms. is equal to, I'm going to take the original two terms here, m1 vi1 plus m2 vi2. And what I have to do is subtract over this term minus m2 vi1 and add over this term plus m2 vi2. Okay. And we'll notice here some groupings. I have things with vi1s and things with vi2s, so we'll group it that way. m1 plus m2 vf1 is equal to, and it looks like I've got an m1 minus m2 vi1. And then looking at here, oh, I've got 2m2 vi2. And so let's finish it off. vf1 is equal to m1 minus m2 over m1 plus m2 vi1 plus 2 times m2 over m1 plus m2 vi2. Okay, and I have my equation. So if you look at that, it looks like the final velocity for object 1 is related to the initial velocities of each of the objects, and then each of those velocities are weighted by some mass-related term. Here it's the difference of the masses over the addition of the masses. Here it's double the second mass over the addition of the masses. Now, if I wanted to do VF2, oof, that would be a lot of algebra. I would have to go back here, solve for VF1, and then plug it in again. But really, that's just the same algebra. So instead, what we want to do is argue by parallelism. We should be able to predict what the term is. Okay. Now, a lot of the same sort of structures are going to happen. So it should not be a surprise that I end up with two terms, one that is VI1 related and one that is VI2 related. Okay. And those two terms are going to be weighted by something as well. And this denominator is going to be the same in both because that just came from, that when we did this distribution, here there was two terms related to the VF1. There's going to be the same two terms related to VF2. So it should make sense that those denominators stay the same. But how is this going to change? Well, if we think about what's going on here, I have m1 minus m2. This is going to become m2 minus m1. And then this would become 2m1. And that is the parallelism argument there, right? That because we're switching what mass we're concerned with, it should make sense that there's some sort of switching going on between those things. These two equations are enormously valuable and should be memorized because if I can show a problem is one-dimensional with the net external force on the system is equal to 0 and the work non-conservative is equal to 0, I can just flat out use these equations in order to solve problems. So in the next video, we'll do some examples of using these equations to solve problems, as well as talk about the meaning of what this equation is and talk about what's happening internally within those, what's happening within that elastic collision. So there we go.